大家好，再过几个小时，也就是北京时间12月28日的17点45分，马斯克的 Starlink 将执行了 V2.0的任务发行。这一次的 Starlink 的卫星发射将标志着两大意义。第一呢，就是这次发射是马斯克在2022年的第60次发射。马斯克的这次发射标志着他在2022年的所有卫星发射与中国的卫星发射的数量是持平的。不过马斯克在今年的12月30日的14点58分，猎鹰9号呢还有最后一次发射，这也就预示着马斯克截止到2022年的总的卫星发射次数是61次，已经超过了中国的所有卫星发射的次数。第二个呢，就是马斯克的这一次 SpaceX 的发射它载着是第二代星链卫星，因为这个卫星的个头比较巨大，张开后的尺寸达到了 12.8 乘 4.1 米，重量呢也高达800公斤，可以直连手机通信。不知道大家是否还记得，就在前几个月马斯克的星链与美国的通讯公司 T-Mobile 当时就共同承诺要实现手机的卫星通信。不过就在当时由于整个星链系统的卫星缺少一个大功率的天线，当时马斯克就已经声称预计在2023年呢实现这个大功率的天线的卫星发射。不过现在看来他这个计划是提前了。这一次的星链卫星的发射仍然呢还是属于测试版的卫星，属于缩小版的 V2.0 的星链，后面呢还将发射重达超过1吨，属于大型的卫星天线。这主要是因为 SpaceX 在向美国的 FCC 提交的申请里也专门写了2个版本。第一呢就是缩小版的，也就是这一次要发射的，其后呢还将发射放大版的。不过这2个卫星分别呢要用猎鹰9号和星舰进行组网发射。为了让大家能够更加清晰地了解星链这个系统的运营系统以及它的技术参数，所以呢我们专门制作了2期，也就是上下集，来向大家介绍一下星链这个系统是如何运营的。在大家了解了这个系统的运营以后呢，我们还将接着来介绍一下明天几个小时以后的星链发射的系统以及对未来的价值和作用。
An extra-large, pizza-sized satellite dish placed on top of your house, up to a satellite orbiting 550 kilometers outside Earth's atmosphere, well, let's be honest, is technologically mind-blowing. What's even crazier is that the Starlink satellites move incredibly fast, around 27,000 kilometers per hour, and data is being sent back and forth between them at hundreds of megabits per second, all while the dish and satellite are continuously angling or steering the beam of data pointed directly between them. On top of that, the dish switches between different satellites every 4 or so minutes because they move out of the dish's field of view rather quickly. If you have no clue as to how this is possible, stick around, because we're going to dive into the multiple key technologies which enable satellite internet to magically work. First, we'll explore inside the satellite dish and see how it generates a beam of data that is able to reach space. Second, we'll see how this dish continuously steers the beam so that it points directly at a satellite moving across the sky. And third, we'll dive into what exactly the dish and satellite are sending inside the beam that results in your ability to stream 5 HD movies or shows simultaneously. This video is quite long as it's full of in-depth details. We recommend watching it first at 1.25 times speed and then a second time at 1.5 speed to understand it as a complete technology. So stick around and let's jump right in. First, let's start by clarifying the difference between a television satellite dish, such as this one, and the Starlink ground dish, which Elon Musk dubbed Dishy McFlatface, or Dishy for short. TV dishes use a parabolic reflector, to focus the electromagnetic waves, which are the TV signals sent from broadcast satellites orbiting the Earth at an altitude of 35,000 kilometers. TV satellite dishes only receive TV signals from space. They can't send data. Dishy, however, both sends and receives internet data from a Starlink satellite orbiting 550 kilometers away. While the Starlink satellite is 60 times closer than TV satellites, it's still an incredible distance to wirelessly send a signal, and thus the beams between Dishy and the Starlink satellite need to be focused into tight, powerful beams that are continuously angled or steered to point at one another. Compare this to TV broadcast signals, which come from a satellite the size of a van, and whose signals propagate in a wide fan that covers land masses larger than North America. Table-sized Starlink satellites, however, need to be in a low Earth orbit to provide for 20 millisecond latencies, which is critical for smoothly playing internet games or surfing the web, and as a result their coverage is much smaller. Thus, 10,000 or more Starlink satellites, all orbiting at incredibly fast speeds in a low Earth orbit, are required to provide satellite internet to the entire Earth. Let's now open up Dishy McFlatface. At the back, we have a pair of motors and an Ethernet cable that connects to the router. Note that these motors don't continuously move Dishy to point directly at the Starlink satellite. They're used only for initial setup to get the dish pointed in the proper general direction. Opening up Dishy, we find an aluminum structural backplate, and on the other side we find a massive printed circuit board or PCB. One side has 640 small microchips and 20 larger microchips organized in a pattern with very intricate traces fanning out from the larger to smaller microchips, along with additional chips including the main CPU and GPS module on the edge of the PCB. On the other side are 1,400-ish copper circles with a grid of squares between the circles. On the next layer, there's a rubber honeycomb pattern with small, notched copper circles, and behind that, we find another honeycomb pattern, and then the front side of Dishy. So, what are we looking at? Well, in essence, we have 1,280 antennas arranged in a hexagonal honeycomb pattern, with each stack of copper circles being a single antenna controlled by the microchips on the PCB. This massive array works together in what's called a phased array in order to send and receive electromagnetic waves that are angled to and from a Starlink satellite orbiting 550 kilometers above. Let's zoom in and see how a single antenna operates. Here we have an aperture-coupled patch antenna composed of 6 layers, most of which are inside the PCB. It looks very different from the antenna of an old-school radio, and is honestly incredibly complicated. So let's simplify it. We'll remove a few of the layers for now and step through the basic principles of how we generate an electromagnetic wave that propagates out from this antenna. To start, at the bottom we have a microstrip transmission line feed coming from one of the small microchips. This transmission line feed is just a copper PCB trace or wire that abruptly ends under the antenna stack. We send a 12 GHz high-frequency voltage or signal to the feed wire, which is a voltage that goes up and down in a sinusoidal fashion, going from positive to negative and back to positive once every 83 picoseconds, 12 billion times a second, or 12 gigahertz. Note that high-frequency electricity works differently from direct current or low-frequency 50 or 60 Hz household electricity. For example, above the copper feed wire, we have a copper circle with notches cut into it called an antenna patch. With DC or low-frequency alternating current, there wouldn't be much happening because the patch is isolated. But with a high-frequency signal, the power sent to the feed wire is coupled or sent to the patch. How exactly does this happen? Well, as mentioned earlier, a 12 GHz signal is applied to the copper feed wire. When the voltage is at the bottom of its sinusoidal or trough, we have a concentration of electrons pushed to the end of the feed wire, thus creating a zone of negative charge which corresponds to the maximum negative voltage. This concentration of electrons on the tip of the wire repels all electrons away, including the electrons on the top of the patch, and as a result, these electrons are pushed to the other side of the circular patch. Thus, one side of the patch becomes positively charged, while the other becomes negatively charged, thereby creating electric fields between the patch and feed wire, like so. However, when we reverse the voltage to the copper feed wire 42 picoseconds later, we have a concentration of positive charges, or a lack of electrons at the end of the wire, and thus the electrons in the patch flow to the other side. The voltage in the patch is flipped, and the direction of the electric fields are also flipped. Because the feed wire voltage oscillates back and forth 42 picoseconds between one peak and trough, the electric fields in the patch will also oscillate as the electrons, or current, flows back and forth. If we pause the oscillation, we can see some of these electric field vectors or arrows from the patch are vertical, and because they're equal and opposite, they cancel out. However, other electric fields are horizontal in the same plane of the patch and are called fringing fields. These fringing fields are in the same direction, and thus they add to each other, resulting in a combined electric field pointing in this direction. At the same time, electrons flowing from one side of the disk to the other, which is an electric current, generate a magnetic field with a strength and direction, or vector, perpendicular to the fringing electric field vector. As a result, we have an electric field pointing one way and a magnetic field pointing perpendicular to that. Let's move forward in time to where the voltage on the feed line becomes positive. And now we're at the peak of the sinusoid, 42 picoseconds later. The charge concentrations, or voltage, as well as the current, is all flipped, and thus the electric and magnetic fields point in the opposite directions. Electric and magnetic fields propagate in all directions, and by creating these oscillating fields, we've generated an electromagnetic wave, which travels in the direction perpendicular to both the electric and magnetic field vectors. Because the two sets of field vectors are not all in the same plane, but rather are curved, the propagating electromagnetic wave travels outwards in an expanding shell or balloon-like fashion, kind of like a light bulb on the ceiling. Let's simplify the visual so we can see the peak and trough, or top and bottom, of each wave, and note that the trough is just a vector pointed in the opposite direction. Additionally, the strengths of these field vectors directly relate back to the voltage and signal that we originally sent to the copper microstrip feed wire at the bottom of the stack. Which means, if we want to make these electric and magnetic fields stronger, we just have to increase the voltage sent to the feed line. It's like a dimmer on a light switch. More power equals a brighter light. Thus far, we've been talking about this aperture-coupled patch antenna as transmitting. However, it can also be used for receiving a signal. In this microchip, called a front-end module, we switch the antenna from transmit to receive and turn off the 12 GHz signal. When an electromagnetic wave from the satellite is directed towards Dishy, the electric fields from this incoming signal will influence the electrons in the copper patch, thus generating an oscillating flow of electrons. This received high-frequency signal is then coupled to the feed line where it's sent to the front-end module chip which amplifies the signal. Thus, these antennas can be used to both transmit and receive electromagnetic waves, but not at the same time. Two quick things to note. First, as seen earlier, this antenna has many more layers and is more complicated than we've discussed. For example, here are two circular patches. The bottom is used to transmit at 13 GHz, while the top to receive at 11.7 GHz. Additionally, there are two H slots and two feed wires to support circular polarization, a reflective plane in the back, and also there are multiple features for isolating the operation of one antenna from the adjacent antennas. We've included these and many more details in the creator's comments, which you can find in the English-Canadian subtitles. The second note is that there are electromagnetic waves of all different frequencies from thousands of different sources, passing through every point on Earth, whether it be visible light from the sun, radio waves from radio or cell towers, or TV signals from satellites or towers. Therefore, in order to block out all other frequencies of electromagnetic waves, these antenna patches are designed with very exact dimensions so that they receive and transmit only a very narrow range of frequencies, and all the other frequencies outside this range are essentially ignored by the antenna. Let's move on and see how a single antenna can be combined with others in order to amplify the beam to reach outer space. This single antenna is only a centimeter or so in diameter, and using only it would be like turning on and off one light bulb and trying to see it from the International Space Station. What we need is a way to make the light a few thousand times brighter, and then focus all the electromagnetic waves into a single, powerful beam. Enter the massive Mr. McFlatface PCB. 55 centimeters wide, with a total of 1,280 identical antennas in a hexagonal array. The technique of combining all the antennas' power together is called beamforming. So, how does it work? Well, let's first see what happens when we have two simplified antennas spaced a short distance away. As mentioned before, one antenna generates an electromagnetic wave that propagates outwards in a balloon shape. At every single point in space, there's only one electric field vector with a strength and direction, and thus, the two antennas' oscillating electric field vectors combine together at all points in space. In some areas, the electric fields from the antennas are pointing in the same direction with overlapping peaks, and thus add together via constructive interference. And in other locations, they're opposite with one peak on one trough, and thus they cancel each other via destructive interference. We can now see that the zone where they add together constructively is far tighter or more focused than a single antenna alone. When we add even more antennas, the zone of constructive interference becomes even more focused in what is called a beam front. Thus, by adding 1,280 antennas together, we can form a beam with so much intensity and directionality that it can reach outer space. Now you might be thinking that the strength of one antenna duplicated 1,280 times over would result in a combined power of, well, 1,280 times a single antenna. But you'd be mistaken. The effective power and range of the main beam from all these antennas combined is actually closer to 3,500 times that of a single antenna. The quick explanation is that by having these patterns of constructive and destructive interference, it's as if we took a single antenna, multiplied it by 1,280, and then placed a whole bunch of mirrors around it and left only a single hole for the main beam to exit through. The long explanation requires a ton of math and physics, so let's move on. Dishy McFlatface and the Starlink satellites undoubtedly have some rather complicated